continuation of another very important module of the chapter electrochemistry. And in this module, we are going to discuss about the applications of Cauchy's law. So the very first application here says that through this particular law, we can calculate the molar conductivity of any electrolyte at zero concentration or infinite dilution. Alright, so here in this graph you have molar conductivity values plotted against square root of concentration for strong as well as weak electrolytes. So for strong electrolytes, we can simply find the lambda naught values by extrapolating the graph, right? But same is not possible for weak electrolytes. So this law is particularly useful to calculate lambda naught of weak electrolytes, as the extrapolation method is not useful for them. Okay, so let us try to understand how we can utilize this law to find lambda naught value of any weak electrolyte. Okay, so we calculate here lambda naught value of acetic acid. Okay, so let us consider that we have been given lambda naught values of HCl, sodium acetate and NaCl, and all these three are strong electrolytes. Okay, so let us see how we can use a combination of these three lambda naught values so that eventually we get lambda naught of acetic acid. Alright, so in acetic acid the ions present are acetate and H plus ions. So let us try to figure out how do we get them. So we have lambda naught of HCl, we add lambda naught value of sodium acetate into it. So these two will be a source of H plus and acetate ions respectively, right? However, we are also getting sodium and chloride ions, which we do not want in the final expression of acetic acid, right? So we subtract lambda naught of NaCl. So simply writing the lambda naught values of corresponding ions. So lambda naught of H plus lambda naught of Cl minus plus lambda naught of acetate ions plus lambda naught of Na plus minus lambda naught of Na plus minus lambda naught of Cl minus. So these are molar conductivities at zero concentration for the ions. So cancelling out the lambda naught values for Na plus and Cl minus, what do we have is lambda naught of H plus lambda naught of acetate ions, which is precisely lambda naught of acetic acid, right students? So we can simply write lambda naught of acetic acid is nothing but summation of lambda naught values of HCl and sodium acetate and subtracting lambda naught value of NaCl. If we know the values of these lambda naught of the corresponding salts which are there, we can easily find molar conductivity at zero concentration for acetic acid. Alright students, I hope this is clear to you all. The next application here is degree of dissociation of weak electrolyte. We can determine the degree of dissociation of weak electrolyte, isn't it? Students, we know that more the number of ions, more will be the conductivity, isn't it? And for a weak electrolyte, as dilution increases, the degree of dissociation also increases, right? Which eventually leads to increase in molar conductivity values, right? So we can say that molar conductivity is directly proportional to alpha, that is degree of dissociation, right students? So at infinite dilution students, we can say that as per Oswald dilution law, degree of dissociation of weak electrolyte is going to approach 1. That means we can say 100% dissociation at infinite dilution students. Alright? So lambda becomes maximum as alpha approaches 1. Right? Thus, we can say that lambda naught is the molar conductivity at infinite dilution, which is going to be maximum value of molar conductivity for a given electrolyte. Then we can say that alpha is nothing but ratio of molar conductivity of given electrolyte at any particular concentration to the molar conductivity of that electrolyte at zero concentration. Alright? So if you know the value of molar conductivity, we can find it through experimental studies. We can find the degree of dissociation of weak electrolyte provided we know the values of lambda naught of a particular electrolyte. I hope students have got a clear idea how do we determine degree of dissociation of weak electrolyte. Going ahead with one more application of Color's law. It is used to determine the dissociation constant of weak electrolyte. Students, we know that for weak electrolyte, dissociation constant mathematically is expressed as alpha square C upon 1 minus alpha, isn't it? So for weak electrolyte, as I told you, dissociation constant K is equal to alpha square C upon 1 minus alpha, wherein alpha is nothing but degree of dissociation, right? And C is nothing but concentration of weak electrolyte. Students, just now we studied that degree of dissociation is nothing but alpha, which is equal to lambda upon lambda naught. So in this particular equation, we can simply substitute the value of alpha, right? So here K is equal to lambda upon lambda naught square C upon 1 minus lambda upon lambda naught, isn't it? So simplifying this particular equation mathematically, what do we get? The final equation as K is equal to lambda square C upon lambda naught into lambda naught minus lambda. So using this equation, we can determine the dissociation constant of weak electrolyte. So I hope students you have got a clear idea with respect to applications of Color's law. Thank you all.